Okay. Topic 6.8. Enthalpy of formation. Let's do this, people. I'll tell you, I just made this whole video and then I made a mathematical error at the end. I forgot to put the negative in front of the number before I added it. And I was like, I knew something was wrong. Glad I figured it out. So let's do this again. You wouldn't even know. All right, so standard. I'm adding the word standard enthalpy. I don't think I'm even going to reference that PowerPoint anymore. However, I will have some practice problems from it. But let's go. Delta HF naught. I think that's 0. That little circle is a naught. So I'm going to erase it because I want it to look nice. All right. Let's see. Delta H, enthalpy. All right. This little circle, standard. So we have the standard enthalpy, F, formation. All right. So we are talking about the energy, right? Energy change for process of forming a compound. 1 mole of a compound from its elements in their standard, and I'll explain all this, state. Right? That's kind of the definition. So I did a good job there, to be honest with you. Incorporated that word standard. So the value for delta HF, all right, is the value that represents the change in energy for the process of forming, right, putting together 1 mole of a compound, and you're putting it together from its elements in their standard state. Because we are forming, will these values always be positive or always be negative? The values will always be positive. No, they will always be negative, right? Because we're forming. And when we form bonds, we release energy. And we don't have to break any bonds to form these bonds, right? Because it's coming from their elements and their standard state. You'll see what we're saying. All right. Now, I want you to realize that if we have elements to compounds, right, and we have a negative delta H, then if we were to reverse, right, to where we had that same compound A, to the elements that formed it, we would have an equal but opposite sign for the delta H. All right? Because I'm going to show you a different way to solve this problem. I'm going to show you, right? That's okay? Because there's an equation, but I don't encourage that you use the equation. I encourage that you utilize this right here. And I'm going to show you what I mean by that. Okay, now let's look at the equation. No, let's look at some equations. So what I have here is from your notes, and right here is an example of a standard enthalpy of formation equation. Notice that 1 mole of product is formed, right? And it is formed from the elements, carbon, standard state, hydrogen in its standard state, and oxygen in its standard state. Now, if you're confused about standard states, we can talk about that for a moment, right? Oxygen is normally a gas, so that is the standard state. Hydrogen is a gas. carbon, as you saw over there, the standard state of carbon is graphite. Another one you may not know is that bromine is a liquid. And then iodine, a halogen, London dispersion forces, purely nonpolar, is bigger than bromine, and he is a solid in its standard state due to the greater polarizability of its with its larger electron cloud. So those are your standard states. Something like silver would be a solid because it's a metal, right? Mercury is a liquid, right? Anyway, you don't need to worry about it. Okay, so let's practice. This is real simple. We are going to write the standard enthalpy of formation for, what's that, methylbromine. I like to start backwards. I'm going to form the compounds and only 1 mole of it from its elements in their standard state. So that's carbon, and I only need 1 carbon. Standard state for carbon is graphite, plus the hydrogen. Standard state for hydrogen is gas. We'll need 1.5 of those in order to keep that balanced. And the standard state of bromine is a liquid, and we'll need 1/2 of that to keep it balanced. So this here would be my standard enthalpy of formation. Once again, it entails that only 1 mole of this can be formed from its elements in their standard state. Now the delta HF for all of these, right, which are all elements in their standard state, the delta HF, the energy released upon forming them will be 0. Okay, so they don't form. They're already present, right? That's how they arrive in nature. Such that the formation here is what it is. It doesn't entail any breaking of other bonds. It's just the formation. And remember, the delta HF here, therefore, will always be negative, right? Will always be negative because all we're doing is forming bonds. They wouldn't form if they weren't more stable, if there was nothing to get from it, right? I mean, someone could argue that to a certain extent. All right. Okay, so let's look at this problem here. This is from your notes, all right? And notice it says pay attention to phases, all right? Because in this one, we have H2O as a gas, and the next one we have H2O as a liquid. So you do need to pay attention to these things, okay? Because notice down here we've got H2O gas and H2O liquid. So make sure that you notice all the details that's provided, all the data that's provided. Now, there's an equation. I'm not even going to tell you the equation because I think, yep, I told you I was going to do both. Delta HF, this is the equation formation. No, okay. Remember, we are getting the enthalpy of the reaction. Look at this. I'm sorry. Checked out for a minute. Calculate the enthalpy for the reaction. Let's look at our data. We have formation data. Last video, last topic, we had bond enthalpy data. We had the bond energy for the HO bond. We had the bond energy for the O2 double bond. And we used those bond energies. We determined, well, am I going to be adding this energy to break it, or am I going to be releasing this energy to form it? Okay, so we use the data as such. This time we have formation data. So you've got to be particular as notice the type of data that you're using to figure out what to do with your numbers, right? Now, right here, you see that I'm going to rewrite this equation right here. And what you need to realize is that And our data is formation data, right? This is formation data. And our first substance here is a reactant. So in my mind, we must unform, right? Now, this is the way I do this without, there is an equation, but if I give you the equation, you're not going to know when to use that equation, because if you use it with the wrong data, you're going to get the wrong answer. So I think, okay, this is a reactant, so I need to unform it, right? Therefore, I must change the sign, change the delta HF standard sign, because the standard sign is for forming, but I'm unforming. The oxygen, this is elemental. This is elemental, therefore the value is 0. So I'm not even worried about that, all right? Now, and then I look over here, I'm like, okay, these are my products, right? So I'm forming. This is a product, therefore I'm forming, right? Therefore, keep data as is. Okay? And the same with this here, okay? So I'm just going to pretend, like I did last time, that I'm dealing with kind of like a bake situation. These will be positive. These will be negative. And I'm going to see, do I put in more or less than I get out? All right? So I've got my CH4. I'm going to clean this up over here. I'm going to find my CH4. And that's CH4 gas, and it takes negative 74.8 is released, but I need to, I'm not forming it, I'm breaking apart, so I'm going to add 74.8, and that's kilojoules per mole, and I happen to have 1 mole of that, all right? And then over here, I've got carbon dioxide, and he's being formed, and my data is formation data. And I see, make sure the gas is the gas, negative 393.5. So that is going to be released. So I'll write negative 393.5. That's kilojoules per mole. And I happen to only have 1 mole again. And then if you look here, change the color, we've got the water, or actually it's water vapor. And we've got 2 moles of it. Water vapor here is that value. So we release negative 241.8 kilojoules per mole, and we've got 2 moles of water, okay? So in this process, we're going to have to add this to separate our reactants. We are going to release, I'm going to do the math over here, negative 393 plus parentheses 2 times negative 241.8 close parentheses equals, that's negative 876.6 kilojoules. All right, so let me make that a little bit neater, negative 876.6. Okay, so what that tells me is that I'm going to put, listen to my analogy, I'm going to put this much money into the bank, and I'm going to take this much money out of the bank. So overall, I'm taking out more, I'm overall negative, and then if I just get the difference between these values, that will tell me how negative I am. So 876.6 minus 74.8. So overall, I have released or removed or withdrawn 801.8 kilojoules of energy, and that is per mole of the reaction as the reaction is written right here. right? So I could make that a thermochemical equation and utilize my mole ratios with my enthalpy. Make sure that you get the negative in there. If you do not incorporate that negative value, it is oh so wrong, right? This is not an enthalpy. The answer is not the enthalpy of formation. The enthalpy of the reaction, it doesn't matter if you write reaction, is negative 801.8 kilojoules per mole, right? You must get that negative in there. That's it. Now, there is an equation. Delta H for the reaction is equal to the sum of the delta H formation of the products minus the sum of the delta H of the formation of the reactants. All right. And when you use this formula, you do not change the sign. Now, if you don't want to listen anymore, you might not want to. But some of you are going to run into this formula and go, well, I'm just going to use that formula. But Miss Murphy said I need to change the sign. No, Miss Murphy didn't teach you to use the formula. Miss Murphy taught you to think, should I change the sign and make it positive, or should I keep it as negative by being logical? These are reactants. This is formation data. I need to undo it. These are products. This is formation. These are products. This is formation. I need to keep it. Now, if you use this equation, which I did not use, you will not change the sign, and that's why you are subtracting them. You will be subtracting a negative from a negative, which means adding, okay? So you can do it that way too. I prefer to think about it this way because if the bond enthalpy is the same thought process, so you don't have to memorize which thought process to apply to different situations. It's the same thought process for all delta H reaction situations. You need to look at the type of data you're given. Is it a reactant? Is it a product? What's going on here? Okay. Thank you.